All right, so now we move on to lesson 7 of equations, and it's solving linear equations by substitution. So this is the point of Math 15, or specifically of equations, when we start moving into content that almost blends into Math 10C. And so what I mean by that is this is actually one of the tools that we will discuss in Math 10C once we get to systems of equations. But for now, what we're going to do is discuss solving linear equations by substitutions, which is one of the methods in which we can compare two equations to one another. So suppose I give you an equation with only one variable in one of the equations. Well, how do we solve this? What we would have to do is consider the example below here. 5x plus 3y is equal to 7, and y equals 4. These represent one equation, two equation, and we're going to want to compare these to one another. Okay, so the steps to solve these are going to be, we have to check if one equation has one variable. And in this case, if we looked at the example below, we would see that equation 2 is that equation. Now, we want to solve for that variable in the equation with only one variable. And in this case, it's already solved for. So when they say if needed, they're saying that if this wasn't already isolated for, we would want to isolate it. Step 3 is to substitute that value into our second equation, or take y equal to 4 and plug it in for our other equation, in this case the top equation. Solve for the second unknown, or the other variable that we don't know. Finally, check your answers in both equations because it must satisfy not only the first equation, but the second equation. So let's see how this works in an example below here. Suppose we give you these two equations here, and we know y equals 4. Well, we're going to take that y and plug it in for our y in the first equation. When we do that, we get 5x plus 3 times 4 is equal to 7. We do a little algebraic work. When we multiply the 3 and 4, we get 5x plus 12 equals 7. We want to isolate for our x term here, so we're going to subtract away the 12. And then finally, we get to a situation once we subtracted 12 where 5x equals negative 5. We divide away the 5 and get x equals negative 1. Now, I really want you to draw your attention to this. When we get an x value like this, it is technically only half of the solution. This is a half solution. Reason being is because in order for it to be a full solution, we have to pair both x and y together. So what do I mean by this? We want to pair them in terms of an ordered pair as the following. An ordered pair is always a solution that includes both the x and the y, and specifically in that order as an ordered pair. So please write that in your notes there, is that ordered pairs are representative of a final solution where x comes before y, and it's written as a coordinate point. Now, what I would like to do actually is see if we could put this in our Desmos software and see if I take these two equations and plug them into Desmos, what is the value I see, or what happens. So let's open our Desmos software here. I'm going to enter those equations here, which they already pre-entered here. And what I should notice is that I have a black line symbolic of x equals 4. So maybe I'll zoom out a little bit just to get our axes in here. We have a black line that is horizontal at y equals 4. We then have a red line that represents our second equation, and it crosses through those lines, or it crosses through y equals 4. Now, what is a solution to any system of equations or two equations when we solve for an x and y? They're talking about a specific coordinate point or a point where the two lines intersect. So in this example, we would see that they cross at -1 and 4, and in fact, that was actually our direct solution from the problem here. We saw that we got a pairing of -1, 4, and that is where they cross over. So when we find these solutions, what are we describing? It's a point of intersection, or more specifically, an ordered pair that represents an intersection. All right, let's try a couple examples here just below. Solve each of the equations using substitution. Well, what did we have to do? We have to take one of the equations and see if they're already isolated for the variable. The nice thing is both of these equations are isolated for the variable, so regardless of if I take this y and plug it in for this y, or the top y and plug it in for this y, I get the same thing. When we do our substitution, if I take the -3 and I plug it in for the y above, I would get -3 is equal to 7x minus 10. I add 10 across to both sides using our previous skills from lesson 1, 2, 3, and even 4. I get 7 is equal to 7x. I know I have to divide by the 7 that's being multiplied to the x. And finally, I have x is equal to 1. There is our solution. Now, we know this isn't a full solution. It's only half of the solution. So in order to get the full solution, now what do? I have to go, therefore, in terms of an xy ordered pair, we get a final solution of 1 for x. And if I go back up to my equation, they already give us the y value. It was negative 3. There's your final solution in terms of a full ordered pair or an x and y. All right, let's go to a second example here, part B. I look at the two equations here and you have to analyze them and say which of these equations, either the first or the second equation, has only one variable. Well, we would notice it's the top equation. So what we're going to do is we're going to recopy that equation out and see if we can isolate for the variable. Negative 6 plus 30 is equal to, I'm going to expand the brackets on the right, 2 times x plus 2 times 3, which is 6. I'm now going to move my variables and my numbers across to isolate. I'm going to add 6 across, and you could equally subtract the 2x from the other side. We then would get 30 is equal to 8x plus 6. If something is being added, then we must subtract it from both sides. Therefore, 30 minus 6 is 24, which is equal to 8x. Lastly, I have a number being multiplied to that x, so I must divide. Therefore, x is equal to 24 divided by 8, which is, in this case, 3. Okay, remember, this only represents half a solution. So what do we have to do now? We've isolated for our x in the top equation. Now, let's plug this value into our second equation and see if we can solve for a specific y. So just off to the right-hand side here, I'm going to take x equals 3 and plug it in. When x equals 3, we get a solution where 3 times that 3 plus 2y is equal to 17. What do we notice? We have an equation in only terms of y, which helps us isolate for y. 9 plus 2y is equal to 17. If I subtract away the 9 from both sides, because I know it's being added, now I get 2y is equal to 8. Some number is being multiplied to that y, so I'm going to divide it, and therefore I get y is equal to 4. But remember, this doesn't represent a full solution yet. We have half and half. We need to put them together as therefore our xy ordered pair is equal to x first, y second. So where these two equations overlap or have an intersection point is where x equals 3, y equals 4. There is our solution here. Now, is this piece necessary to the solution? Not really, but what I always think is I want to prep you for final exams, diplomas, multiple choice questions, and it's always important that we put our x before the y. So sometimes writing the order like this is going to help us arrange our information in the proper order. It's going to make sure that we don't make a mistake of saying, oh, well, maybe it's y before the x. No, we always want to maintain that order of x, y, where x comes before the y. All right, let's go over to a couple more examples here. I look at these two equations here for C. This one has two variables. The top equation has one variable. So we're always going to start with the equation with one variable. I go negative 10 is equal to negative 8x over 5 minus 2. Now what we should realize is that we have an LCM of 5, or the lowest common multiple of the denominators is 5. So we're going to multiply both sides by 5. When I multiply both sides by 5, I'll get negative 50 on the left is equal to, well, 5 divided by a 5, when I expand this in, because I want to take the 5 and distribute that 5. When I distribute the 5, 5 divided by 5 eliminates the 5 in the denominator and the numerator, and I am left with negative 8x. And then negative 2 times 5 is negative 10. I'm going to add that 10 across that's being subtracted, giving me a result of negative 40 is equal to negative 8x. And now I have this negative 8x that must be divided away from both sides. So therefore, x is equal to a negative divided by a negative gives me a positive, and 40 divided by negative 8 gives me 5. Remember, this is only half the solution now. We have to take this x value and plug it into the second equation to get y. So what I'm going to do off to the side here is say we have 2 times 5 over 5 minus 16 is equal to 2 times, in brackets, 5 plus 12y, all in brackets. When I have this 5 divided by 5, I know 5 divided by 5 is 1. I get 2 minus 16 is equal to, I'm going to expand the 2 into the brackets or distribute the 2. That gives me 10 plus 2 times 12y is 24y. And now I want to collect some like terms on the left-hand side. 2 minus 16 is negative 14, which is equal to 10 plus 24y. And now I'm going to take that 10 and subtract it away. It's being added, so I'm going to subtract it. Negative 24 is equal to positive 24y. And finally, 24 is being multiplied to y, so I'm going to divide it from both sides. And so I get negative 24 divided by a positive 24 gives me my final solution. Y is equal to negative 1. Now, remember, these have to come together to make my solution. Therefore, my ordered pair xy is equal to x first, y second. So I get an ordered pair of 5, negative 1, and that is my solution there. If you stop short and you say x equals 5, y equals negative 1, and this is a written response, you haven't shown me that these come together to represent a point on a graph. All you've said is, yes, I've calculated the values, but how do they come together? They come together as an ordered pair or a specific point where these two equations overlap. All right, and now let's go to the U-try section. Very, very similar to our last problem here. We want to look at these two equations and say which equation only has one variable. We have this equation with just x's and this equation with xy. We know we're going to start with our first equation. 4x plus 13 is equal to 2x minus 7. I'm going to subtract my 2x across, I get 2x plus 13 is equal to negative 7. I'm going to subtract away 13 from both sides, giving me 2x is equal to negative 20. And now I have a number being multiplied to the x, so I divide. X is therefore equal to negative 10. Now, this is half a solution. Remember, only having x is half a solution, or only having y is half a solution. We need to take this x value and plug it in for the equation we have here, or our second equation. When I do that off to the right-hand side here, I'll get negative 9 times that negative 10 minus 12y is equal to 42. Now, I get positive 90, because a negative times a negative is a positive. We get positive 90 minus 12y is equal to 42. And now we go, in order to isolate this, I'm going to take the 90, subtract it across because it's being added, subtract 90, I get negative 12y is equal to 90 minus 42, we should get 48. And then I'm going to divide by, and I need to make sure I include the negative here, because we have more negative than positive. 42 minus 90 is negative 48. Lastly, I have to divide by the negative 12, divide by the negative 12. Therefore, a y is equal to positive 4. Now, in order for this to be the final solution, I have to say, now, therefore, in terms of an xy ordered pair, this is equal to x first, or the negative 10, and then 4 second. There we go, highlight the solution. Now, remember what I said about this. We just need to have the ordered pair here. That would technically get you full marks, but it's sometimes nice to write the xy in front of it just to make sure that we're organizing the data properly. All right, now, what if we go to equations with two variables? So considering the following example, we see that both equations have an x and a y. So here's where our step differs a little bit. We need to check for an equation that only has a variable with a coefficient of 1. So if I look at these two equations here, well, I would realize that x has a coefficient of 1, so that would be the term I would want to isolate for. So if needed, we would isolate it. In the case below, we don't really need to isolate x because it already is, but we may have to isolate it there. We're going to substitute that variable, just as we've done before, into the other equation, solve for that variable, substitute the value we get from substituting that first value, And then finally, check our answers in both equations just to make sure. Okay, so let's look at our example below. We're given the two equations, 3x minus 7y equals 14 and x equals 2y minus 3. The nice part is we've already isolated for this x here, or already been given an isolated term. So we're going to take everything x is equal to and plug it in for x. When we do that, we get a term, or we get an equation with everything in terms of y. When we make that initial substitution, you should realize you have everything in terms of one variable, because as soon as you get this scenario, you know you're on the right track because now you can isolate for that variable. When we do our algebraic work with the equation, we would get y equals 5, and we have to remember this is only half a solution. Once we get our y equals 5, we're going to take it and substitute it back in for the equation that x is equal to, or one of the equations, and isolate for x. And when we do that, we get a value of x equals 7. And then finally, we would get an ordered pair of 7, 5 that could be checked in both equations to make sure that the left-hand side equals the right-hand side. Let's try a couple examples here. So we're going to flip over our page to 53, or in your books, I believe 52. And so let's skip past here. We're actually going to see some direct examples in action here. Now, if I look at these two equations here, first equation, second equation, I realize they both have two variables. The nice thing is we already have one of the equations isolated for a variable with a coefficient of 1. So what we're going to do here is I want you to circle everything that y is equal to here and put an arrow down to the y in the second equation. Why is that? Because we're going to go x plus 2 times everything y is equal to. 3x plus 2 is equal to 11. Now, what do we have here? An equation in terms of one variable, which is exactly what we need here. So we have x plus 2 is going to be distributed into every term in the brackets here. So I get 6x plus 4 is equal to 11. When I add the terms together, I have 7x's plus 4 is equal to 11. If I subtract that 4 across in order to isolate the x term, I now have 7x is equal to 7. And finally, I know I need to divide away the 7, that is the coefficient term, finally leaving me with x is equal to 1. But just as before, what do we realize? This is only half a solution here. When x equals 1, that's only given us the x value. We need to solve for the y. So we're going to go back up to this first equation that described y and say that y is equal to, we're going to substitute the value for x, which was 1. Therefore, y is equal to 3 plus 2, which is 5. And as an ordered pair, we say that x and y is equal to x first, so 1, y second. There we go. Now, we could check this solution by plugging it into both equations. So just to show you what it means to verify or check, if we want to verify that this is the solution, we have to plug it in for both equations. Meaning, I'm going to start with my first equation. We had y is equal to 3x plus 2. When I plug in x and y, I have 5 is equal to 3 times 1 plus 2. Therefore, 5 is equal to 5. So perfect, we've proved it. Now, let's do that with the second equation as well. X plus 2y equals 11. X plus 2y equals 11. Substituting the values in, we have 1 plus 2 times 5 is equal to 11. Well, 10 plus 1 is definitely equal to 11. There we go. We verified that both equations are satisfied with a point of 1, 5. Okay, now let's go on to example B. Nice thing is we get another equation where we have a coefficient of 1 that's already isolated for. So, I mean, technically what we could do is we could look at this second equation and go, okay, we have an x value that's also a coefficient of 1. But if they give us something that's already isolated, let's use that. So we're going to say everything that y is equal to is going to get substituted in for the y value. X plus 3 times the 2x minus 3 is equal to 5. When I distribute this 3 into the brackets, I get x plus 6x minus, and in this case 9, is equal to 5. I add my like terms, which is 7x's minus 9 is equal to 5. I'm going to add the 9 across because it's being subtracted, so I get 7x is equal to 14. And now I have a 7 that needs to be divided away. So I'm going to divide both sides by the 7, therefore x is equal to 2. Remember, this is only half a solution. We need to take this x value and plug it in for our equation to get our y. So off to the right-hand side here, y is equal to 2 times that x value, 2 minus 3. If I do 2 times 2, that's 4, minus 3 is 1. Therefore, my ordered pair in terms of x and y, which I'll move this way a little bit, x and y, is equal to 2 first, 1 second. There we go. And of course, we could do the verification step that we did on the first problem here, but I don't think it's directly necessary unless they specifically ask us, or if we have any doubt with these answers, we could always check them. But for the most case, this is more than enough just to solve for the solution here. All right, now we go down to C. Our life is a little more difficult with these ones because we don't have a variable isolated. So what we have to do is we have to go between equation 1 and equation 2, which variable has a coefficient of 1. And what you would do is you would correctly identify that x here in the first equation has a coefficient of 1. So this is going to be the equation that we isolate a variable for, x minus 2y. So we're going to go x minus 2y is equal to negative 6. When I isolate for x, I add the 2y across to both sides, and I'll get x is equal to 2y minus 6. Okay, now that I know what x is, I can take everything that x is equal to and plug it in for the x in the second equation here. So I'm going to underline this in blue, underline our x in blue to show what we're doing here. We're substituting 4 times everything x is equal to. 2y minus 6 plus 6y is equal to negative 4, or positive 4 in this case. What do we realize? We have an equation in terms of one variable, so now we can solve 8y by distribution, 4 times 2, 4 times negative 6, 4 times 2y is 8y, 4 times negative 6 is negative 24, plus 6y is equal to 4. When I collect the like terms or the y terms on the left, I get 14y minus 24 is equal to 4. And now I'm going to add the 24 across, add the 24 across. This gives me 14y is equal to 28 total. I therefore now need to divide by the 14 that's being multiplied to y. And finally, I get y is equal to 28 divided by 14, which is 2. Now, this is only half a solution, but what I realize is that I have the x in terms of y above, so what I can do is say, if y equals 2, let's plug it in for this equation, and then that will give us the x value here. So off to the right-hand side here, what I'm going to do is say, when y is equal to 2, what do we have? X is equal to 2 times that 2 minus 6, or x is equal to 4 minus 6, which is negative 2. So now we have our ordered pair. Therefore, in terms of an x and y ordered pair, it is equal to negative 2 and 2. There is our answer here. Now, what we could do is we could verify it just like we had in example A. We could take any of the values and we could take these values, negative 2 and 2 for x and y, and plug them into both equations and show that the left hand equals the right hand for both of these equations. But that would be more of a task for you to try to make sure that you're doing these steps correctly here. All right, now let's go on to example D, which uses the similar concept as C. We don't have a variable isolated for, so what we have to do is look at our first equation and our second equation and say, which one has a coefficient equal to 1 on its variable? Well, we would realize in equation 1, we have a y value of 1y, so we're going to isolate for that y. 3x plus y is equal to negative 7. I'm going to subtract the 3x away and subtract the 3x away, therefore leaving me with y is equal to negative 7 minus 3x. Now, we know the value of y in terms of x, so we're going to plug this in for our y in our second equation. When I do that, the following is negative 2x plus 4 times everything that x or y was equal to is equal to 0. And so I get negative 2x plus, when I distribute this 4, I guess I shouldn't assume that there's going to be a plus because the signs are going to be impacted here. We have 4 times negative 7, which is negative 28. 4 times a negative 3 is negative 12x, which is equal to 0. Negative 2x minus 12x is negative 14x. Minus 28 is equal to 0. I'm going to move the 28 across that's being subtracted to isolate our y term, or isolate our x term, I should say. Negative 14x is equal to 28. I divide by the negative 14 on the x, that's the coefficient, and now I have x is equal to 28 divided by negative 14, or negative 2. Now, this is only half a solution, so what do I need to do? I need to take the x value I found and plug it in for the equation that will help me get y. So when x is equal to negative 2, I'll do it off to the right-hand side. When x is equal to negative 2, we plug it into the equation y is equal to negative 7 minus 3 times the negative 2. So we get y is equal to negative 7 minus 3 times 2. That's like saying negative 7 plus 6, which is negative 1. So now our solution in terms of an ordered pair of x and y is equal to negative 2 and negative 1. And so maybe I'll write it below just to give us a little more space here. Therefore, in terms of an ordered pair xy, we have negative 2 and negative 1 because x always comes before the y here. There we go. Okay, so now you get to check your understanding. This is definitely the type of lesson I would get lots of practice with. Definitely try and complete as many of these check your understandings as possible.